Okay, hello everyone. So now we've talked about the Timmett principle. What does that mean in terms of agent-based modeling? Well, let's first talk about what agent-based modeling is. Agent-based modeling provides us a way to model individual level interactions. It gives us the ability to represent each agent in our system as a computational entity within the computer itself. So we could essentially take what we might say in vivo, in a large group setting of, say, people wandering around at a conference talking to each other about what they plan and hope to do that evening for dinner. And we can replicate that as an in silico model, right? So we take the in vivo and we turn it into in silico. Traditionally, agent-based models were built from very simple rules derived from theory. So, for instance, Thomas Schelling, one of the first users or creators of an agent-based model, created a simple model of segregation patterns in the United States by saying that everyone has a slight preference to live near other people. But he used the checkerboard as his actual original simulation environment. It wasn't really a computer at all. And he used pennies and dimes to represent different ethnicities, and he kind of moved them around in this space. It wasn't really tied to data at all. If we could create agent-based models that were directly tied to big data, we could create an individual level detailed model that was derived directly from the digital traces that we talked about, right? If we had these right tools, then we could eventually maybe even have the ability to create what you might think of as an ABM directly from the data, where we just give it the data, it creates an ABM, it comes up with theories or rules about what the behaviors are, and then we could evaluate those theories and rules, right? Rather than just using some black box like a neural network where we pump a bunch of data and get a prediction out. This would be akin to something both John Holland and John Sterman. John Holland was one of my advisors. John Sterman is a complexity theorist in the business schools, in the business world, mainly publishing out of MIT. And they called these tools policy flight simulators, right? So the ability to explore what would happen if you put different public policies in place in these spaces, right? Much like a flight simulator, they don't perfectly represent the world around us, right? You can't exactly say that a flight simulator translates directly to flying a plane, but they give you a feel for what it's like, right? They give you a feel for what that policy might happen. However, in all these cases, we still want to make sure that the model is theory interpretable. In fact, we'd want to be able to seed the model with theories, right? We'd want to be able to say, hey, don't just pull any theory out of this big data or put any rule out of this big data, but try and use these particular theories to explore it. And what I'm going to talk about here is various approaches that allow us to do that. So, for instance, we could use, the more general area that I call data-driven agent-based modeling, which is any agent-based model where data is used to increase the validity of the model and the tools and methodologies that are developed to help facilitate the validation of models with that data. So not just the data created with this model, but also I'll include all the methodologies and pedagogy around how do you construct a data-driven agent-based model. So let's take a step back and talk about what is validation. Validation, and can mean different things in different fields. I tend to approach it from a computer science perspective, which is where my training is. My PhD is actually in artificial intelligence from Michigan, and so I like to think of it in that case. And in computer science or in software engineering, we often talk about two notions: verification, which I'm not going to talk too much about today. Verification is making sure that your model is doing what you think it's doing, right? That the implemented model corresponds to the conceptual model you have in your head. And validation is making sure that the implemented model, the agent-based model or whatever computer model you're building, corresponds in some meaningful way to the real world. And within the concept of validation, I like to think of kind of two axes. One is face validity, and the other is empirical validity. And face validity is, does the model on its face, like the basic rules and behaviors, if you were to describe it to someone who kind of knew a little bit about that phenomenon, say, oh yeah, that corresponds. And within that, you could talk about microface validation. Does the agent make a decision the way an agent would in the real world, right? So if you go back to like Schelling's model, which I briefly mentioned as segregation, maybe the basic rule of behavior is okay, but the pattern of where people live in Schelling's model is a pure checkerboard, and that's not doesn't really reflect reality. So you could say that on face, the rule of behavior is valid, but maybe the actual neighborhood model isn't necessarily on face valid. Now, just because a model doesn't is is not valid in every kind of concept that you could come up with doesn't make it invalid. Validity is a spectrum, right? That goes from a model that has no kind of correspondence to reality to a model that fully corresponds to reality. And so you're just somewhere on that spectrum. And so, for the point of view that Schelling was trying to achieve, the validity level that he achieved was perfectly fine, right? And then we have macro face validation, right? Do the process and patterns of the implemented model correspond on face to the real world? One way to think of this is in the end, Schelling's model creates a pattern of segregation. That was something that we observed in the real world and still do, right? And so to some extent, the macro face validity was fine. Then we could talk about empirical input validation. And so the other side of the coin is empirical validation, where face validation is, does this kind of look like what we expect it to look like? Empirical validation is where we actually take real data, calibrate the model or look at the model, look at how the inputs and the outputs relate to real data, and we show that they are. And so empirical input validation is making sure that the data used as inputs to the model corresponds to the real world, whereas empirical output validation is making sure the output of the model corresponds to the real world. And this can be done in a number of different ways. Again, you can kind of get almost like a face validation where you have subject matter experts look at the pattern and say, yes, that output is what we would expect it to be, right, in some respects. You go a little bit closer and say, does some macro measure of the real world correspond to what we're seeing? So for instance, in the segregation case, if we could measure how likely it was for one ethnicity to live next to another ethnicity in the real world, and then look to see if Schelling's model replicated that, for instance. And of course, there's even cross validation, which is comparing our model to a previous model that has already been validated in some way. Okay. So now that we have this notion of validity, let's talk a little bit about what the different aspects of this are. So the um, way that this has been done in the past has been done in a number of different ways. And one of the oldest models is this model that really showed empirical validation or data-driven validation was the Anasazi model. And this was a model that was developed at the Santa Fe Institute back in the late 90s and eventually wound up getting developed into this paper that got put out in 2002. The essential question they were trying to answer is that there was a group of Native Americans living near Santa Fe in the Kayenta, or they were the Kayenta Anasazi. They were living near the Longhouse Valley in New Mexico, and they did this model of how the Native Americans lived in that population. And the question they wanted to know is what drove the collapse of this population, because you see evidence in the Anasazi for a long time in the Longhouse Valley, and then they just suddenly disappear. And so they created this model to kind of explore that question and explore a number of different theories people had. Like, was it water supply? Was there a drought, right? Was it a invading neighbor, right? Was it some other a disease or something like that that caused it to break out? And they tried to come up with different theories and explore how well they matched the underlying data. And they were able to, in the original paper, they were able to kind of throw away a couple of theories that maybe didn't match the data very well, but in the end, they really weren't able to come up with a great answer as to what was the best exploration. And it seems like there must have been an exodus or a migration pattern that occurred at some point because they couldn't come up with another theory that really affected what's going on. In other words, at the end of it, maybe after the population declined due to lack of water or something else, right, a large group of the Anasazi just left the valley, and there doesn't seem to be another great explanation. But this people keep going back and forth on this one, so you might read a different paper explaining a different hypothesis on this very soon. So this is one of the first kind of really well done empirical output validations using an agent-based model. A paper I was able to work on was one in 2005 where we took a model of residential land use around the Washtenaw County, which is a county in southeastern Michigan, and we explored trying to predict future land use based upon current patterns of behavior. And the goal of this project was to eventually look to see how we could implement different policies that would both allow us to achieve certain human welfare goals, like people living where they wanted to and close to where they were working, but also at the same time having less of an impact on the environment around them. And so we built a bunch of different agent-based models that used GIS data to kind of start the model up and running, and then we would compare that to a future prediction. So in this case, what you're seeing in the top left corner is a single realization of our model, and the single realization isn't something you want to look at in a lot of these agent-based models because often you want to do multiple runs to kind of fully explore what's going on and to see what's happening. But it's helpful to kind of look at like what does it typically look like, or what is an example of it looking like. On the B kind of panel, you're seeing how often the model predicts a certain space in the county would be developed. And in the C, we created something we called the variant invariant region. So the white areas are areas where the model never predicts development. The black areas are where the model always predicts development, and the gray areas are where sometimes there's development and sometimes they're not. And of course, indeed, we have the actual reference map of what we are trying to predict. And in this case, we did a fairly good job of doing this, but it kind of provided us with a number of different tools, or we created a number of different tools like the variant invariant to kind of better inform policymaker decisions in this space. There was some great work that I've always liked to talk about that comes out of a group called Sirad and Cormas in the early 2000s, where they would actually have participants in a variety of different spaces come in and work with um, models of land use development in their neighborhoods, right? And so, for instance, some of this was done with Thai rice farmers, right? Where they would come in and talk about how they would use water to feed their crops. And then those rules of behavior that the humans expressed would then be embedded into an agent-based model. The model would then be played out, and those results would be presented back to the farmers so they could see how their different rules of behavior would affect the development of these landscapes. I've gotten really interested in this recently. I think I want to go back and explore some of this work and maybe look at how, with modern AI systems, we can continue to do this. Like, if we're interacting with an AI system for policy, could we use a participatory simulation method in order to better understand how our inputs might affect the governance patterns of an AI system that's controlling, say, water distribution or traffic flow or something like that? So, how do you actually go about doing this? How do you actually go about empirically validating a model? One way is through what we call parameter optimization. This is the simplest way, and this is kind of the way that the Anasazi model took to some extent, right? Where we have a real world, right, and we have the model, and we take some training data from the real world about what's going to happen, and we run the model, we predict what's going to happen, and then we change our parameters, a process we call calibration, so that the actual model outputs better match the real world, right? So in the case of Project Sleuth, right, we could take our model, set it up, and then we could see how well the prediction of the variant invariant regions matched up with the actual instantiation of the real world, and then we could alter some of our parameters about like how likely people like to be close to city centers or different things like that to see what the effect would be on the real world environment. And this is fine and dandy to some extent, right? It requires us, it doesn't use a lot of the big data because in the end, we're not actually building the model from the data. We're just using the model to kind of calibrate a theory. We're just using the data, sorry, to calibrate a theory we have about the way the real world works. Um, so, an example of this that's kind of really clear is this is actually a bunch of data of social media activity around a hurricane that is about to hit the east coast of the United States. And you can actually see the hurricane going up the east coast on that little red dot in the gray path on the right-hand side. But what you're going to eventually see is some green dots starting to appear, and those are donations to the American Red Cross from people worried about this hurricane that's hitting the East Coast. And as you can see, most of it happened after the hurricane actually hits the coast, right? But what if we wanted to predict this pattern, both the donations, but also the social media activity that happened in that space? How can we go about doing that? Well, one way would be to build an agent-based model of social media activity. And one of the interesting things about social media activity is it's greatly informed by social behavior, right? It's informed by the other people you're seeing on the networks. So we went and we took some very simple models of information diffusion that had basically all of them had two parameters, a P and a Q value. And P is like, how likely am I to talk about this hurricane just because I want to talk about hurricanes. And Q value is more like how likely am I to talk about a hurricane because all of my friends are talking about a hurricane, right? And there's a number of different models that kind of fit this space. There's something called the BAS model, which comes out of marketing, and there's the independent cascade model, which also kind of comes out of marketing in some respects, but more related to network diffusion. The threshold model of Granovetter also kind of works in this space as well. We could talk about that. We didn't explore that in this particular paper. We have explored that in others. And what we could do is we could kind of explore all the different values of this P and Q parameter in these different modeling setups, and we can see where does the pattern of information diffusion we see on Twitter best match what the model predicted. And as you can see, both of these models, both the mass model and the cascade model, for two different hurricanes. So on the top we have Hurricane Irene, and on the bottom we have Hurricane Sandy, which is the one I showed you. There is a big space where the P and the Q values kind of settle down. And those are the darkest blue areas because that's the where we have the smallest error between the model and the actual prediction. And this kind of gets you the ability to understand kind of how quickly does information diffuse and how much of it is socially driven versus being driven by, say, advertising or something external to the social media network. So that's parameter optimization. But nowadays, a big interest I have is in what I'll call rule induction. So unlike parameter optimization, where we were kind of focusing on the micro level parameters, the focus in rule induction is in identifying macro level patterns and rules of behavior. So can we just, rather than, using the BAS model or the cascade model, can we just speculate about the different types of basic actions people might take and then see if there is a role that best describes those actions based upon data that we see around us? So one initial approach that we tried was to use something called epsilon machines or causal state models. That was kind of really explored by Cosma Shalizi and Jim Crutchfield to a large extent. And this is actually part of a lot of Cosma's PhD dissertation. And so in these cases, we assume that some time series we're observing is a conditionally stationary stochastic process. In other words, that the data that we're observing is represents a pattern of behavior that is stationary, it's not changing over time, conditioned on recent behavior that we've seen in the past, right? So if we know, say, the last 10 time steps of behavior of actions you've taken, then we'll be able to make a good prediction about what action you're likely to take in the future. And what's cool about this particular approach is that we can explicitly learn the predicted distribution by grouping together paths that have a similar future. In other words, let's say we're trying to predict whether you're going to tweet about Hurricane Sandy or not, right? And we in the past time period we've seen you not tweet, tweet, not tweet, tweet, right? But in other cases we saw you tweet, not tweet, tweet, not tweet, and both of those, even though they're different histories theoretically, have the same possibility of you tweeting in the next time step, right? Then we can group those together into the same state. They represent the same state of the world. Using this simple kind of this simplest approximation, um, Cosma and Jim developed something called the causal state splitting and reconstruction algorithm, which allows you to automatically develop these models directly from data. And what's interesting is that Cosma showed in his dissertation that these models are maximally predictive and minimally complex. In other words, they do the best job of predicting the future that any algorithm you could for that particular data set could do without knowing something about the data. And they are minimally complex. In other words, they have the fewest possible number of these different states of similar futures. So we took that and we were able to use it to make predictions about social media behavior. We then used a similar framework. We kind of added some additional thoughts to it and things like that to create a full model of social media actions. And in this case, we developed this for a project called Social Sim, where we were trying to predict all sorts of different social media platforms, whether it be Reddit or Twitter, or I think we played around with some Telegram data at times, right? About a variety of different topics, whether it be cryptocurrency trading schemes to the China One Road, One Belt discussions, right? To a lot of different areas that we were exploring. And we were able to use agent-based modeling to kind of infer rules of behavior about the different actions that people might take in this space. And then use that to update the agent's actions and beliefs, and then allow them to take external actions based upon that as well. And we never really got fully into the external action space, but we were able to do a good job of predicting what people were doing in terms of just posting on social media and social media activity and who they were sending things to. And this project did pretty well. This model did pretty well in a variety of competitions where we actually did compete against other people who are making predictions about the same social media space. So I believe that if we can truly model individual level goal-driven users well automatically using some of the approaches I've talked about today, then we could potentially take these models and embed them in a full simulation of whatever system we are interested in understanding. This would enable the creation of a large-scale data-driven model that could be updated regularly and automatically, similar to something we talk about when we talk about digital twins nowadays. Digital twins is the idea that we can create a full-scale representation of a physical system in silico that we can then play around with. One of the great examples I've seen of this is that Hong Kong's airport maintains a digital twin of the airport so that if a plane is late, they know exactly how that's going to affect all the other gates and aspects of the world, right? I think such a model could really be used as a proxy for reality, to explore an almost infinite number of possibilities of policy and procedure in this space. And if it worked well with social media, then we can expand it to other streaming data sets. For instance, an entire city that had been implemented with smart sensors. And that would allow for the creation of a true policy flight simulator, a la John Holland and John Stern that we talked about at the beginning. I think, in reality, if the agent-driven, agent-based modeling was applied in this dynamic fashion, we could create really amazing models, right? And that these models might even look a little bit like what Isaac Asimov talks about in his Foundation series when he discusses psychohistory, right? This idea that we can make predictions about full-scale social trends in the world around us. I also think that these models have the potential to avoid something called the Lucas critique. So the Lucas critique comes out of the macroeconomic literature, and essentially the Lucas critique says any model you have about a policy change that you're planning to implement in economics is going to be false because it was developed in a world where that policy didn't exist. So let me give you an example. If you're thinking about a new tax policy, say you're going to tax, you're going to tax capital gains at a different level or in a different way than you were doing it before. Um, the models of how the stock market works and how the economy behaves are all trained on data where that policy did not exist, right? And so, therefore, if you make a prediction about how that policy is going to affect things, it's going to be wrong, according to Lucas, because the models aren't taking into account this new policy. This what this critique assumes is that the way you've modeled agent behavior at the lowest level doesn't reflect the actual goals and desires of agents that you have in the real world. And so therefore they will find ways around this policy. They'll find ways to evade the new capital gains tax, for instance, right? But if we actually model individuals at the lowest level, if we model individuals at the level where we talk about what their goals and desires are, then we have the potential to evade the Lucas critique, right? Because the Lucas critique does not assume that the agents in our model are accurately responding to changes in the environment the way their goals and their directed beliefs say they should. Now, it's really hard to prove, right? Because you'd have to prove that you have your agents are open to any potential changes you might make in the environment. That's almost impossible to really show in a valid way. But I do feel that the more level matching that you have within your model, the more the macro patterns match and the meso patterns match and the micro patterns of match, the less likely you are to fail prey to the Lucas critique. And this could be the best possible solution for predicting macro scale policy effects. So with that, I'll sign off. If you have any questions, feel free to shoot me an email. And thank you very much for your time. Take care. Bye.